Okay, so good morning everyone. Uh, so today we will carry on our discussion of complexity of basic arithmetic operations. So last class we saw that addition and multiplication. So we saw the complexity of adding two numbers, and then we also saw the complexity of adding n numbers, that is iterated addition, and that essentially gives us a bound on multiplication as well. Okay. So today we will continue looking at other operations, other basic arithmetic operations, and try to analyze their circuit complexity. But before that, let me just formalize some circuit classes. So we have been actually talking about these circuit classes, but we haven't formally defined them. So let me start by defining these bounded depth circuit classes. Okay. So essentially these classes consist of Boolean functions which can be computed by bounded depth circuits which have a certain structure. Okay. So the first definition that I want to introduce is that of non-uniform classes. So a function f from 0 1 star to 0 1 is said to be in the non-uniform class, let us say some C, some arbitrary class, if there exists a family of circuits Cn, okay, indexed by n. So basically by family what we mean is an infinite family. So C1, C2, C3 and so on, such that for all x belonging to 0 1 to the power n, f of x equal to c. Let me use a different index here, cm of x. Okay. So essentially we have been, again, so we actually saw this earlier as well, but I am just formalizing this. Essentially this says that a general function, okay, so a function which can have inputs of arbitrary size. So I have a star over here. Now we say that this function is said to be computable, is said to be non-uniform C. So C can be any class if there exists a family of circuits such that for all x of a fixed length, okay, the value of that function on that input should be why do I have this was the comma, so the value of that function should be what the corresponding circuit outputs on that input. Okay. So this is what is non-uniform. So essentially the only thing that we are given is the existence of such a family. So this family need not be constructible, and we say that it is in uniform C if this family can be constructible as well. Okay, so we have notions of log space uniformity, we have notions of other uniformity as well. So logs, for example, if I say it is log space uniform, it means that this family can be constructible, I mean is constructible by a log space Turing machine. Yeah, so basically given n, so there is a log space Turing machine which given n can build Cn in log space. Okay, we'll come to that later. We don't need that right now. Okay. So, now moving on to some circuit classes. So, first let us say NCI. So, this is the class of Boolean functions computable by bounded Fanon circuits over, let us say, or and not having polynomial size and order log to the power in depth. So, NCI is all circuits which have bounded Fanon and polynomial size and log to the power in depth, okay, over and or not gates. Actually, this is not a very strict requirement. Even over any even over B2 also one can show that it can be reduced to circuits which have only and or and not gates. Okay. And NC is basically the union over all NCI for I greater than or equal to 0. So, typically we will look at the class NC1, NC2. So, NC1 is basically circuits which have log depth, NC2 circuits which have log square depth and so on. Now, we have the class ACI. So, ACI is exactly the same, but instead of bounded Fanon we allow unbounded Fanon. Okay. So, basically we can have an AND and OR gate which can take arbitrary number of inputs, okay. And the definition is of course very natural. So, if you have an AND gate with a k inputs, it outputs 1 if all the k bits are 1, and an OR gate with k inputs will output a 1 if at least one of them is a 1. Okay. So, ACI is the class of Boolean functions computable by unbounded Fanon circuits over OR and NOT gates having poly size and order log to the power in depth. Okay. And analogously, AC is union over all ACI for I greater than or equal to 0. Okay. So, before we go forward, let us just try to answer a few things. For example, last time we saw that addition. Okay, we looked at the problem of addition of two strings x and y. What is the so in which class is addition? What is the complexity of addition? It is in NC1 because we showed that it can be done by linear sized circuits having log depth, right. What about iterated addition or what about multiplication? again it is NC1 because we showed it is in log depth and it has polynomial size. So, I will actually come back to that problem a little bit later, but let me move forward. Okay. So, the next definition that we will see is about a function. So, these are function classes. So, let me define the threshold function. Okay. For x1 to xn belonging to 0 1. Okay, so, these are bits. This function threshold of x1 up to xn, let me just check the definition. Okay. Threshold of x1 up to xn is equal to 1 if a1 x1 plus a2 x2 plus an xn is greater than or equal to some theta and equal to 0, otherwise where a1, a2 up to an and theta does not depend on the x's, okay. But it can depend on n though. Okay, so, let me just explain this. So, what we are saying is that, so basically we have this threshold function which takes n bits and it will output 1 if basically this sum a1 x1 up to an xn is greater than some theta and equal output 0 otherwise. And these constants, so think of these a1 up to an and theta to be constants. So, they are constants because they do not depend on the specific input, they do not depend on the x's, right, but they can actually change with n. So, maybe for some n equal to 1 you have some a1 and you have some theta, for n equal to 2 you can have some different set and so on, but for the respective x's they do not change. Okay. So, they are constants for a fixed n. Okay. So, now we can define the class TC. Okay. So, TCI is the class of Boolean functions computable by polysize and order log to the power in depth circuits having threshold gates only. Okay. So, now if I say that a circuit, I will allow a circuit only to have threshold gates. Okay. So, TCI is basically all the functions that can be computed by such circuits which have polynomial size and log to the power I n depth. Now you might be wondering that what about other gates, I mean what about AND or NOT and these other basic gates. So the point is that any of those gates can actually be simulated using a threshold gate. Okay, so we can actually see that. So for example, how would you simulate a OR gate using threshold gate? Exactly. So you take the AIs to be 1 and theta to be 1. So setting for all I, AI equal to 1 and theta equal to 1 gives us the unbounded Fanon OR gate. Okay. What about AND? So an AND gate must have all its input as 1, right? Exactly. So basically for all I, you have AI equal to 1 and you set theta to be n. What about NOT? So a NOT gate will always have a single input. Okay. So what do you set A1 to be and theta to be? So one way to do it is, I mean there are many ways to do, but one way to do it is setting A1 to be -1 and theta to be 0 will give you NOT gate. Okay. No, A1 1 and theta 1 will not give you NOT gate. So it will be 1 if and only if xi is equal to 1 or x1 is equal to 1, and it will be 0 otherwise, right? It will be the same thing. Okay. So essentially the point is that, so threshold gates actually can, you can build any of these basic gates using threshold gates and probably more. Okay. So now, what about another, we can try another one. What about the majority function? So majority is when, so a majority gate will, the majority function outputs say 1 if at least n by 2 inputs are 1. Okay. Again it's simple, so you set all the AIs to be 1 and theta to be n by 2. Gives you the majority function. Okay, so now what are the relations among these classes? Okay, so we have these classes that we have defined, NCI, ACI, PCI and so on. So what are the relations? So by definition we have, what do we have? So we have that NCI is contained in ACI, right? Because it's bounded, this is unbounded, and because we just saw that AND OR and unbounded AND OR and NOT can be simulated by threshold circuits, we have that ACI is in TCI. Okay, but one can also show that TCI is actually in NCI plus 1. So if you add another log n layers, you can actually not log n, actually you add another multiplicative factor of log n layers, then actually you can do TCI as well. And the way to prove this is, so I will just leave this as an exercise, this is not difficult. You can show that the threshold function, okay, so this is in NC1. Okay. So once you show threshold is in NC1, you can actually replace every threshold with a log n depth circuit, and then for any TCI you will get a NCI plus 1 circuit. Okay, and this you can think about it. Again, the idea is not very difficult, because so what are we doing? So essentially we are doing addition, we are doing iterated addition, right? We are multiplying with a constant and we are doing iterated addition and we are doing one comparison. So you have to think how you can do all of that. So iterated addition we have already seen, but comparison you have to think how you can do that in NC1. Okay. So any questions? I will just come to that. The answer is yes, you can do parity, and I will just come how you can do parity using threshold circuits. Okay. So before moving forward, just a small correction from something that I said last lecture. Okay. So last lecture what all did we see? Okay. So let me just quickly recap what we did last lecture. So we saw that given two numbers x and y, okay, let me just write that. We saw that given two numbers, we can do x plus y in what kind of complexity. So we saw that using this parallel prefix sum method, we can do this using a bounded fan-in. Okay, so a circuit which uses only AND, OR and NOT gates, bounded fan-in circuit having log depth and linear size. Okay, so this can be done in NC1. So this is something that we saw. What about iterated addition? So suppose if I have m numbers x1, what notation did we use? Did we use xi's or ai's? So what notation did we use last time for iterated addition? Xi's, right? Okay. So if we have m numbers x1, x2 up to xm, okay, where each xi is a n bit number, and we want to compute sigma xi. So what was the complexity of this operation? So what we said last time is that this is this can be done by a circuit which has order of log n plus log m depth, and how much was the size? So order mn. So this is what we said last time. Okay, but this is actually not quite correct. Okay, so actually it is size mn. So this log n factor doesn't appear, because just, I mean, let me just, if you just carefully look at the analysis, you will realize this. Okay, so let me just write it over here. So this is actually in size mn and not mn into log n. So the reason is, so how did we do this addition? Okay, so we have these numbers, right? So we have x1, x2, x3, 4, x5, x6, so on up to xm, and we took them in blocks of 3. Okay, and then we reduced this to two other integers. Okay, so we reduce the sum of x1 plus x2 plus x3 as the sum of some two other numbers, right? That is what we did. Okay. So let's say in the second level we reduce this to something like x21 and x22. For this we got x23, x24, and the last one was m by 3. So we will have something like x2 2m by 3 minus 1. Let me put a comma over here, and x 2m by 3, something like this, right? So, and to do this, okay, so here, so basically we are coming from, so here we are doing some m by 3 additions. Again here we will club them into groups of 3 and so on. So how many additions will we have here? So here we have a total of 2m by 3 numbers. Again we club them into groups of 3. So we will have 2m by 9 many additions, right? So we will have something like 2m by 9. So in the next layer we will have, again we will do the same thing. So we will have something like 4m by 27. Okay. So essentially the total number of such additions will be sigma two to the power I m divided by 3 to the power I plus 1. Okay. This is actually the total number of additions, and if you actually solve this, so m comes out, what you get is sigma 2 to the power I over 3 to the power I plus 1. This is actually a convergent series. Okay, so this, I mean, in fact 2 to the power I plus 1 divided by 3 to the power I plus 1 itself converges to 3, right. So this is actually even smaller than that. So essentially this is order of m, and each addition we saw by the this method, that if you have any two numbers, each addition takes order n time. So the total size is order n size. So the total size is order nm. Okay. So the calculation that we did last time, it was a very brute force calculation. So for each level we assumed we have order m many summations, but that is not so. It is basically decreasing at each level. Okay. So therefore iterated addition can be done or can be computed by bounded depth, not bounded, what I want to write is bounded Fanon circuits in order nm size and order log n plus log m depth. Okay. Clear? One more very interesting point about this thing is that what is this size as a function of the input size? How much is the circuit size as a function of the input size? Is it linear? Is it quadratic? So look at the input. We have m numbers. What is each number? How many bits does it have? Each number has n bits, right? So what is the size of the input? it is nm, right. So, actually what we are getting is the optimal, okay. So, actually what we are getting is an nm size circuit, order nm size, okay. So, it is actually linear in the size of the input, right, and it has logarithmic depth. Okay.
Why is that depth log n plus log n?
Each addition will take log n many log n depth, and the depth there are log m. So, this depth, okay. So, basically the way this this addition works is you show that if you take any 3 numbers, okay, you can represent the sum of those 3 numbers as the sum of 2 other numbers, okay. So, you club them into groups of 3, and essentially initially you have a total of m many numbers, then in the next level you have 2m by 2m by 3 numbers. So, this is basically coming down one level, and now you keep on doing this. So, in the next level you will have 4m by 9, then you will have 8m by 27 and so on. So, basically this will, you keep on doing this until you have just 2 numbers left, and the number of levels you need to do this is order log n.
Each addition is now replaced by a sum of two circuits.
Which addition are you talking about? This addition?
Yeah, at each level.
Yeah.
So, and there are log m depth.
Yes.
Many additions.
Yes.
Oh, right, so yeah, addition.
Huh?
It should be addition.
Huh. Yeah, so this is something that I just wanted to clarify. Okay. Any other questions? Order of n square, yeah. No, it is not order of n square, it is order 2n actually. So, n plus n, right? No, but you are multiplying 2 numbers. Here you are adding, sorry. Sorry, yes. Multiplication will be order n square, yeah. So, multiplication is still not optimal, yeah, correct. Absolutely. Well, the input size is twice n, exactly. So, you have two n bit numbers, so let us say you have x and y, which has size 2n, and you are showing that there is a circuit of size order n square which is doing. I mean, it is not optimal. I mean, I am not saying that it is not optimal, but I am saying that it can possibly be lower.